Electrochemistry. This chapter has the main three parts: electrolysis, standard cell potential, fuel and battery, the relationship of F equals L times E. F equals Faraday constant, L equals Avogadro constant, and E equals charge of electron. Faraday constant equals the amount of charge in 1 mole of electrons. Avogadro constant equals the number of electrons in 1 mole substance. 1 electron has charge equals E. L number of electrons has the charge equals L times E, Coulomb. This is actually Faraday constant. So F equals LE. Example. From data booklet, Avogadro constant, L equals 6.02 times 10 to the power 23. The charge of 1 electron, E equals minus 1.602 times 10 to the power 19 C. So, L times E equals 6.023 times 10 to the power 23 times minus 1.602 times 10 to the power 19 Coulomb equals 96,488.46 Coulomb. This is near to 96,500 Coulomb. This is Faraday constant, F. Example 1. Calculate the mass of silver deposited at the cathode during the electrolysis of silver nitrate solution if you use a current of 0.10 amps for 10 minutes. The solution. The amount of charge, Q equals I times T equals 0.10 times 10 times 60 equals 60 Coulomb. From the equation at the cathode, we can say that to deposit 1 mole of silver we need 1 mole charge. From 96,500 Coulomb charge, silver deposited equals 1 mole equals 107.9 gram. So, from 60 Coulomb charge, silver deposited equals 107.9 times 60 divided by 96,500 equals 0.067 gram, which is deposited at the cathode. Example 2. Calculate the volume of hydrogen produced, measured at room temperature and pressure, RTP, during the electrolysis of dilute sulfuric acid if you use a current of 1.0 amp for 15 minutes. The solution. The amount of charge, Q equals I times T equals 1.0 times 15 times 60, time is in second, equals 900 Coulomb. From the equation at the cathode, 1 mole hydrogen gas deposited for 2 moles of electrons. From 2 times 96,500 C charge, hydrogen gas deposited 1 mole equals 24 decimeter. So from 900 C charge, hydrogen gas deposited equals 24 times 900, 2 times 96500 decimeter, equals 0.11 decimeter. Standard electrode potential. The electrode potential is the measure of individual potential of reversible electrode at standard condition compared to standard hydrogen electrode, SHE. Chemical energy changes. Electrical energy produces due to the chemical energy changes. Electrical energy is the voltage produced. This is actually electrode potential. At standard condition, this called September. The SEP is measured by comparing with the reference electrode. So to find the SEP we have to connect with SHE. Then the circuit will be completed. Standard conditions. The concentration is 1.0 mol/dm3. The pressure is 1 bar, 100 kilopascals. The temperature is 298 Kelvin, 25 degrees centigrade. Here are a few typical standard electrode potentials. All are reduction potentials. Some are positive and some are negative. Negative potential means the backward reaction is favored in the equilibrium. Magnesium ion is more stable than metal, so backward reaction favored. More reactive metals give great reduction potential. All these data will be given standard hydrogen electrode. This is a reference electrode. Hydrogen gas is used here at standard conditions. The standard conditions are: pressure 1 atmosphere, temperature 298 of Kelvin, concentration 1 mole per cubic decimeter. Platinum wire is used as a support. To increase the surface area, platinum foil is used. There is an equilibrium reaction between hydrogen ion and atom. Standard cell potential. The cell potential is the measure of the potential difference between two half cells in an electrochemical cell. The units of the potentials are typically measured in volts. Standard cell potential of standard hydrogen electrode and standard magnesium electrode. These two are connected by a wire. There is a voltmeter between these two. The voltmeter shows the potential difference between these two half cells. To balance the ions, these two cells are connected by the salt bridge. It is used to connect the oxidation and reduction half cells. If no salt bridge were present, the solution in one half cell would accumulate negative charge. It does not react with any of the chemicals used in the cell. Calculations of standard cell potentials. This is the most important part of this chapter. When individual cell potentials are given, the cell potentials can be calculated. Calculations of standard cell potentials of copper-magnesium cell. The electrode potential given for copper is positive 0.34 volt. This is a reduction reaction. The electrode potential given for magnesium is negative 2.38 volt. This is also a reduction reaction. For calculations of the cell potential, keep the larger reduction potential fixed. Then add another one by making the sign opposite. Positive 0.34 is larger, so it kept constant. Then negative 2.38 volt is converted to oxidation potential by changing the sign. Now, the first one is the reduction and the second one is oxidation. Adding these two we get cell potential. So the cell potential is 0.34 volt plus 2.38 volt equals 2.72 volt. Calculations of standard cell potentials of copper-magnesium cell. Using the number line. The electrode potential given for copper is positive 0.34 volt. This is on the right side of 0 in the number line. The electrode potential given for magnesium is negative 2.38 volt. This is on the left side of 0 in the number line. The geometric difference between these two is the cell potential. The RMO8 entered 2.72 volts, which is shown in the number line. Important notes about standard cell potentials. If cell potential is greater than 0, the forward reaction is favored. If cell potential is less than 0, the backward reaction is favored. For example, for copper-magnesium cell potential is positive 2.72 volts. So the overall equilibrium reaction is forward directing. Nernst equation. This equation is used to find the potential of the cell at any temperature. The related terms are E equals cell potential at temperature T. E standard equals standard cell potential at standard condition. R equals molar gas constant, 8.31 J per Kelvin per mole. N equals number of electrons transfer, also called Z. F equals Faraday constant, 96,500 Coulomb. The concentration of the oxidized substance and reduced substance will be given. Nernst equation for the specific redox reaction of copper and silver. Copper loses 2 electrons and silver gains 1 electron. To make the equation balance, we multiplied the silver batteries and fuel cells. There are 3 main parts of this section. They are hydrogen-oxygen fuel cell, nickel-metal hydride rechargeable batteries, lithium-ion cell rechargeable batteries, hydrogen-oxygen fuel cell. It needs hydrogen gas and air. The hydrogen enters the fuel cell at the anode. A chemical reaction strips the hydrogen molecules of their electrons and the atoms become ionized to form H+. The electrons travel through wires to provide a current to do work. The oxygen enters at the cathode, usually from the air. The oxygen picks up the electrons that have completed their circuit. The oxygen then combines with the ionized hydrogen atoms, and water is formed as the waste product which exits the fuel cell. The reactions involved in a fuel cell are as follows. Anode side, an oxidation reaction. Hydrogen ions produced from hydrogen gas. Cathode side, a reduction reaction. Oxygen gas combines with hydrogen ions and makes water. Net reaction, the redox reaction. Hydrogen gas plus oxygen gas equals water, nickel-metal hydride rechargeable batteries. A nickel-metal hydride battery, abbreviated NMH, is a type of rechargeable battery. The chemical reaction at the positive electrode. By using nickel oxide hydroxide, the negative electrodes use a hydrogen-absorbing alloy, lithium-ion cell rechargeable batteries. A lithium-ion battery is a type of rechargeable battery in which lithium ions move from the negative electrode to the positive electrode during discharge and back when charging. Lithium-ion batteries use an intercalated lithium compound as one electrode material. The electrolyte, which allows for ionic movement, and the 2 electrodes are the constituent components of a lithium-ion battery cell. Advantages of fuel cell. Fuel cells are the smaller size. They have lower mass and they have a higher voltage.